Okay, let's dive right into this explainer on what I like to call the ultimate chemical paradox, fluorine. We are going to explore a story of incredible danger, miraculous utility, and an environmental puzzle that scientists are still desperately trying to solve today. You see, fluorine is a master of absolute extremes. And to truly understand how it shapes our modern world, from the life-saving medicines in our bathroom cabinets to the water in our lakes, we have to look at the chemistry that makes this element so completely unique. Think about this for a second. The 19th century history of scientists just trying to tame elemental fluorine is incredibly deadly. For over 70 years, some of the absolute greatest minds in chemistry tried, and failed, to isolate it. Because fluorine is so violently reactive, it just destroyed their glass and metal equipment. And tragically, several scientists were literally blinded or even killed in the process, earning them the pretty grim title of the fluorine martyrs. It actually wasn't until 1886 that a French chemist named Henri Moissan finally succeeded using a specialized platinum apparatus. It was such a massive breakthrough that it earned him a Nobel Prize. Section 1. The reactive beast, the chemistry of elemental fluorine. So why is it so dangerous? Well, it all comes down to electronegativity, which is exactly why fluorine oxidizes almost everything it touches. On the Pauling scale, which measures an atom's ability to attract electrons, fluorine sits at the absolute top with a perfect 4.0. It is literally the most electron-hungry element in existence. It reacts at room temperature with almost all other elements. It'll even aggressively attack normally unreactive precious metals like gold and platinum. It's just a chemical beast that entirely refuses to exist peacefully on its own. Section 2. The carbon-fluorine bond, Dr. Jekyll emerges. Here is where things get really wild. When fluorine is bonded to itself as a gas, that FF bond is surprisingly weak. It breaks apart effortlessly because those small atoms are actually repelling each other with their electron lone pairs. But when that incredibly electron-hungry fluorine bonds to carbon, everything changes. The electron density is pulled heavily toward the fluorine, creating a polar bond with this massively powerful electrostatic attraction. The result? It becomes virtually indestructible. It forms what is widely considered the strongest single bond in organic chemistry. It's like a chemical Mr. Hyde turning into a perfectly stable Dr. Jekyll. And as you add more fluorine atoms to a carbon atom, this partial ionic character starts acting like molecular superglue. It tightly strengthens the bond with every single fluorine you add. If you start with just one fluorine and fluoromethane, sure, the bond is strong. But as you add a second, a third, and finally a fourth fluorine to create carbon tetrafluoride, the bonds physically get shorter, and the energy required to break them just skyrockets. They essentially lock the carbon atom down into an impenetrable chemical fortress. Strangely enough, the quantum mechanics of hyperconjugation make these molecules bend into highly stable formations. Now, normally in organic chemistry, big, bulky atoms on adjacent carbons hate being crowded together. They want to be as far apart as possible. But fluorine, it totally bends the rules. Because of a quirky phenomenon called the Gauss effect, the atoms actually prefer a bent adjacent conformation. The orbitals overlap and share electron density in a way that gives them even more structural stability, making these molecules just incredibly durable. Section 3. Harnessing the power, medical and industrial miracles. Okay, so how do we actually use this unbreakable bond? Well, substituting a standard carbon-hydrogen bond with a much stronger carbon-fluorine bond prevents life-saving drugs from breaking down too quickly in our bodies. In fact, roughly 15% of all new pharmaceutical drugs contain at least one fluorine atom. Why? Because the human liver has such an incredibly hard time metabolizing it. This means the active ingredients in your medications can stay in your system longer, allowing for lower doses and much better absorption. It really is a genuine medical miracle, and it relies entirely on fluorine's unique grip on carbon. Section 4. The rise of PFCs, the return of Mr. Hyde. But, there's always a catch, right? This chemical invincibility led directly to the massive industrial boom of PFCs, or perfluorinated compounds, starting back in the 1950s. Manufacturers quickly realized that long chains of these carbon-fluorine bonds repelled literally everything, both water and oil. They became wildly popular overnight. They were sprayed on waterproof clothing, woven into stain-resistant fabrics, baked into nonstick cookware, and poured into heavy-duty firefighting foams. They were everywhere. But the very property that made them so incredibly useful, the fact that they simply do not degrade, became their absolute fatal flaw. Section 5. Forever chemicals in nature, the bioaccumulation crisis. Stepping out of the abstract chemistry for a second, let's look at the real world. When you look at a pristine, scenic view of a place like the Great Lakes, it's crazy to think it might be hiding an invisible chemical threat. But because PFCs don't break down naturally, they are completely persistent in the environment. Recognizing this emerging danger, the EPA launched massive studies in the 2000s to track these so-called forever chemicals. They began to realize these compounds were broadly distributing across aquatic environments, quietly accumulating in beautiful natural places, just like the Great Lakes. The sheer scale of the EPA's sampling here is honestly staggering. When testing fish tissue across 157 randomly selected near-shore locations throughout the Great Lakes, what they found completely shifted our understanding of the risk. It turns out, eating fish from contaminated waters is actually a primary source of human exposure to these chemicals. The PFCs were slowly moving from the water, into the fish, and ultimately straight onto our dinner plates. And this is the crucial point. What happens when these chemicals actually get into our blood? They take a massive biological toll when they bioaccumulate. Because they are practically designed to be unbreakable, our bodies just cannot get rid of them. Today, the vast majority of people living in industrialized nations have detectable levels of PFCs in their serum. Elevated concentrations have been linked to severe health effects, immunotoxicity, thyroid disease, high cholesterol, endocrine disruption, and some truly alarming potential cancer risks. The invincibility of the carbon-fluorine bond has officially become a severe liability to human health. Section 6. Breaking the Unbreakable, the Scientific Frontier. So how do we fix this? Well, chemists are basically having to resort to intense chemical brute force, using targeted radiation and exotic metals just to rip that fluorine away from the carbon. You can't just burn or bury these chemicals. To destroy them, scientists are engineering extreme environments. They're bombarding the molecules with UV light paired with specific sulfites, utilizing cutting-edge photocatalysts or employing highly reactive metal complexes like zirconocene dihydride, just to force that bond to finally break. It's a colossal effort, and frankly, it is one of the most pressing challenges in environmental chemistry today. So I'll leave you with this final paradox to think about. As the strongest bond in organic chemistry continues to shape both our lifespans and our environment, we've seen how fluorine went from a violently dangerous gas to the foundation of life-saving medicines, only to spawn these indestructible forever chemicals that literally haunt our water supplies. Can science invent a way to keep the miracles of fluorine while entirely erasing its environmental curse? It's a massive question that researchers are racing to answer right now. And the outcome? Well, it's going to impact generations to come. Thank you so much for joining me for this explainer.